On July 2nd, 2025, something exploded in deep space that shouldn't have been possible according to every model astronomers had for how these events work. It didn't last seconds. It didn't last minutes. It kept firing for 7 hours, then again the next day, then again after that, before finally fading into an afterglow that lingered for months. Astronomers agree on one terrifying detail. A black hole ate a star. What they can't agree on is exactly how. Gamma-ray bursts are the most violent explosions the universe produces, capable of releasing more energy in a fraction of a second than our sun will emit across its entire 10 billion year lifetime. Most are over almost as soon as they begin, gone in seconds, occasionally stretching into a few minutes at most. They typically come from one of two sources, either two neutron stars colliding, each one no bigger than a city, or a massive star collapsing in on itself after burning through its nuclear fuel. Both processes create a newborn black hole, and some of the infalling material gets funneled into narrow jets, blasting outward at nearly the speed of light, producing the gamma-ray flash astronomers detect from across the universe. Astronomers do already know about a rarer subset of these events called ultra-long gamma-ray bursts, ones that stretch past 1,000 seconds instead of fading within minutes, and researchers have built models over the years to account for at least some of that extended duration, usually involving a massive star's core collapsing more slowly than the typical case. GRB 2507002b doesn't just belong to that rare category, though. It blows straight past it. At roughly 25,000 seconds of gamma-ray emission, it lasted about 25 times longer than the threshold that already defines an event as unusually prolonged, putting it in a category of duration nobody had previously observed directly, let alone built a confident model to explain. GRB 2507002b broke that pattern completely. It was first picked up by China's Einstein probe satellite in X-rays, then confirmed by NASA's Fermi Gamma-Ray Space Telescope, along with the monitor of all-sky X-ray image, the CONUS Wind instrument, and the Space Variable Objects Monitor, giving researchers multiple independent confirmations rather than a single, possibly unreliable detection. Its gamma-ray emission alone lasted roughly 25,000 seconds, close to 7 hours, making it the longest gamma-ray burst ever recorded, dwarfing every previous event in the catalog. It didn't fire once, either. It erupted in 3 distinct bursts spread across an entire day, with irregular gaps between flares ranging from about an hour to as long as 25 hours, before finally settling into an afterglow that continued to be detectable for months afterward. Having that many separate instruments independently confirm the same event matters enormously here, because it rules out the possibility that this was some kind of glitch or misread signal from a single piece of hardware. Each of these observatories operates completely independently, built by different teams, calibrated through entirely separate processes, and monitoring different, only partially overlapping slices of the electromagnetic spectrum. When 5 separate instruments all pick up the same extraordinarily long, extraordinarily energetic CE event within the same general window, that convergence is exactly the kind of evidence that turns a strange anomaly into a genuine, confirmed astrophysical discovery worth building entire research papers around. If watching real astronomers argue over genuinely unresolved cosmic evidence rather than a settled, tidy explanation, is exactly the kind of story you come here for. Go ahead and subscribe, because that's the territory this channel covers. Researcher Brendan O'Connor, who led one of the analyses of this event, put the core problem plainly. GRB 2507002b is a genuine outlier. It doesn't fit any standard explanation for how gamma-ray bursts are supposed to behave. Scientists broadly agree on the headline conclusion that some kind of black hole consumed a star to produce this event. What they don't agree on is which specific scenario actually happened. And that disagreement has produced several genuinely competing published explanations, each backed by real data and real modeling, none of them fully able to claim victory yet. One leading team, led by researcher Eliza Nates and dozens of co-authors, published their findings in the monthly notices of the Royal Astronomical Society, proposing what's called the helium merger model. Under this scenario, a black hole already existed in a binary system alongside a companion star that had been stripped down to mostly helium, having already lost its outer hydrogen layers earlier in its life. As that binary system aged, the black hole and the stripped star spiraled closer together until the black hole finally fell into the star itself, consuming it from the inside out over an extended period rather than in one single instantaneous collision. That gradual internal consumption process would naturally explain why the burst stretched on so much longer than a typical gamma-ray burst, since the black hole wasn't just briefly forming and firing a jet. It was actively working its way through an entire star's structure over a period of hours. A separate, competing team has proposed something almost as dramatic, but built around a different kind of stellar object entirely. Their model suggests GRB 2507002b was produced when a white dwarf, The dense, burned-out core left behind after a sun-like star exhausts its fuel wandered too close to an intermediate mass black hole and was to RN apart by its tidal forces. Intermediate mass black holes occupy a genuinely elusive category in astrophysics, sitting somewhere between the stellar mass black holes formed from individual collapsing stars and the supermassive black holes anchoring entire galaxies, a category astronomers have struggled for years to confirm examples of with real confidence. Under this scenario, the extreme gravitational tidal forces of the intermediate mass black hole would have stretched and shredded the white dwarf as it approached, generating exactly the kind of prolonged, highly variable X-ray and gamma-ray activity observed across the following days. This particular model carries its own extra layer of significance beyond just explaining one unusual burst, because confirming even one solid example of an intermediate mass black hole would answer a question astronomers have been chasing for decades. Researchers have long suspected these medium-sized black holes must exist somewhere, since it seems physically implausible for black holes to jump directly from stellar mass to supermassive scale without anything filling the gap in between. But confirmed, uncontested examples have remained frustratingly rare. If the tidal disruption explanation for GRB 250702b holds up under further scrutiny, this single event could end up serving double duty, both explaining one of the strangest bursts ever recorded and providing one of the clearest pieces of evidence yet that this missing category of black hole genuinely exists out in the universe, not just in theoretical papers. A white dwarf makes for a particularly interesting candidate for this kind of disruption too, precisely because of how dense it already is. Unlike an ordinary star, which a black hole's tidal forces would tend to rip apart relatively gently from a considerable distance, a white dwarf packs roughly the mass of the Sun into an object only about the size of Earth, meaning a black hole has to G considerably closer before its gravity can overcome the white dwarf's own intense internal gravity holding it together. That closer approach translates into a far more violent, more energetic disruption once it finally happens, potentially helping explain why this particular event produced such an extreme, prolonged burst of high-energy radiation rather than a more modest disruption event. Both models share a genuinely important piece of supporting evidence. Follow-up observations, using the Very Large Telescope and the Hubble Space Telescope, managed to resolve the host galaxy surrounding GRB 250702b, confirming the event happened far outside our own galaxy, and crucially, that the explosion occurred noticeably offset from the center of its host galaxy rather than sitting right at its core. That detail matters enormously because it effectively rules out one other possible explanation researchers initially had to consider: a supermassive black hole, the kind that sits at the center of essentially every galaxy, tearing apart a star that wandered too close to it. Since GRB 250702b happened away from its galaxy's center, whatever black hole caused this had to be a smaller wandering object, either a stellar mass black hole in a tight binary system or an intermediate mass black hole, drifting somewhere within the galaxy's outer regions, rather than the supermassive giant anchoring the galaxy's core. Pinning down that offset position required genuinely careful observational work, since resolving a specific point of light against the diffuse glow of an entire distant galaxy, billions of light years away, is a considerably harder task than it might sound. Researchers needed sharp enough imaging to distinguish the burst's precise location from the galaxy's own central bulge, and confirming that distinction cleanly enough to rule out a supermassive black hole took dedicated follow-up time on two of the most powerful optical telescopes currently available to astronomers. It's worth understanding just how unusual it is for a single astronomical event to resist explanation this thoroughly, given how many separate research teams have thrown serious analytical firepower at the same dataset. Researchers studying GRB 250702b found a hard energy spectrum, meaning the gamma rays carried unusually high energy, combined with variability on timescales of a fraction of a second, buried inside an event that otherwise stretched on for hours, alongside an overall energy output that researchers describe as only being explainable by ultra-relativistic jets powered by a rapidly spinning central engine. Taken together, researchers analyzing the event concluded that these specific properties, combined with the sheer duration involved, are simply incompatible with every confirmed gamma-ray burst progenitor previously cataloged, and nearly incompatible with every theoretical model currently sitting in the scientific literature. That last point is worth sitting with for a moment because it's a genuinely rare thing for working astrophysicists to say plainly about real observational data. It's not that GRB 250702b is merely an extreme version of something already well understood. It's that the event's specific combination of extreme duration, rapid internal variability, and total energy output doesn't cleanly match any existing theoretical framework researchers had built before this event arrived. That's precisely why multiple serious, independently published papers have proposed genuinely different physical mechanisms, a helium-star merger in one case, a white dwarf tidal disruption in another, each one internally consistent with at least some of the observed data, without either fully explaining every single detail recorded across the event's unusually long, complicated timeline. The broader detective work behind identifying this event's host galaxy and its precise offset position also deserves real credit, since it took genuinely difficult patient follow-up observation across multiple instruments to pin down, confirming an extragalactic origin, ruling out a supermassive black hole at the galaxy's core, and narrowing the field down to either a stellar mass black hole binary or a wandering intermediate mass black hole all required careful cross, referencing between X-ray, gamma-ray, radio, and near-infrared observations, gathered by an entire international network of telescopes and satellites, coordinated in the hours and days immediately following the initial detection. Non-detections mattered here, too. Several observatories searching for corresponding signals in visible light and in very high-energy gamma rays found nothing, and those absences turned out to be just as scientifically useful as the actual detections, helping researchers rule out entire categories of explanation that would have predicted signals showing up in those specific wavelengths. It's worth being clear about what remains genuinely uncertain here, since a story framed around the most extreme object ever recorded can easily drift into overstatement. Every research team studying GRB 2500702b agrees on the fundamental headline: a black hole consuming stellar material produced this event, and that it represents something genuinely new added to the astrophysical catalog, an event long enough and energetic question whether existing models for gamma-ray bursts were actually complete. What remains unresolved is the specific mechanism, whether this was a black hole slowly consuming a stripped helium star from within a long-standing binary system, or an intermediate mass black hole tearing apart a wandering white dwarf through tidal disruption, or possibly some third explanation nobody has fully worked out yet. Multiple credentialed research teams have published peer-reviewed papers defending each of these competing scenarios, and as of the most recent published analyses, no single explanation has become the clear scientific consensus. Step back far enough, and this becomes a story about how much genuine mystery still exists in observational astronomy, even when the underlying event gets detected by 5 separate instruments, confirmed across multiple wavelengths, and analyzed by dozens of researchers working independently across different institutions. GRB 25072b sits billions of light years away, its light only reaching Earth's detectors after traveling for longer than complex life has existed on our own planet. And even with that much data, that much instrumentation, and that much collective analytical effort, astronomers still can't fully agree on exactly what happened when it went off. That's precisely what makes it worth paying attention to. Not because anyone has definitively cracked the case, but because watching serious researchers openly disagree over genuinely ambiguous, high-quality data is a far more honest picture of how astrophysics actually progresses than any single tidy explanation could ever offer. There's a decent chance this particular argument doesn't get fully resolved anytime soon, either. Confirming which specific scenario actually happened would likely require catching another event with a similar signature and enough advance warning to point additional instruments at it, while it's still everything after the fact. From archival data the way researchers have had to do here. Until then, GRB 2507022b sits in the scientific record as confirmed, extraordinary, and only partially explained. Exactly the kind of unresolved case file that keeps astrophysicists arguing at conferences for years afterward. If deep dives into real, currently unresolved cosmic mysteries like this are what you come here for, make sure you're subscribed, because there's a lot more of exactly this kind of ongoing scientific debate still playing out in real time. And if the idea of astronomers agreeing something ate a star while still arguing over exactly what and how surprised you, let me know in the comments which explanation you find more convincing, and I'll see you in the next one.